Hello everyone. In today's class, we are going to discuss another metric for green chemistry, that is E-factor. In the previous lecture, we discussed about atom economy or atom efficiency, which was a factor which is more of a theoretical thing which we calculate from the balanced chemical equation of a reaction. E-factor is more related to the quantity of the waste, and it is more of a practical thing, like you do the reaction and then you calculate the E-factor, and it is associated with the first principle of green chemistry, which states that it is better to prevent waste than to treat it up after it is formed. So E factor is associated with the quantity of waste generated in a chemical reaction or a process. This concept was given by Rogers Shelton in 1992, and it is defined as the total mass of the waste divided by the total mass of the product. It is the E factor actually stands for environmental factor. So it is related to the environmental impact of any chemical reaction, which comes in the form of the waste that is generated during a process. So here the focus is on the waste that is generated. Ideal E factor for any chemical reaction or process is 0, because zero waste is the target, and it cannot be calculated theoretically. You have to do the reactions to see what is coming out of the reaction, how much water is being produced, how much of the solvent is being used up, what type of emissions are there, that we will explore in the subsequent slides. So what was the need actually for introducing an environmental factor or E factor? So the industry is basically driven by economy, like profit. So the focus is not on the environmental impact. So in 1992, there was a plant which was associated with the synthesis of fluoroglucinol using these steps which are shown on the slide. So when they were using this strategy or this multi-step synthesis to synthesize fluoroglucinol, so what happened is that the amount of waste generated in this process, it becomes so large that the money which is spent on the waste disposal, it kind of like approaches to the value or the profit which is generated by selling this product. So the waste generated was becoming a problem. Just to give you an idea, like 40 kilograms of the solid waste was generated for every kilogram of fluoroglucinol which is produced, and that waste comprised of chromium sulfate, ammonium chloride, ferrous chloride, and potassium hydrogen sulfate, etc. So if you look at it, they were using all the traditional synthesis type of the steps, like using potassium dichromate and sulfuric acid, which are not environmental friendly. And similarly, a metal with the hydrochloric acid, carbon dioxide is emitted, which is a greenhouse gas, then using again hydrochloric acid. So it means that the process, it inherently was not green, and it was generating a lot of waste. So this plant has to be shut down. So then they introduced this factor which can kind of give you a mental image of the waste. Like just by quoting the E factor, you can get a view of like this much wasteful this process is, and then you can look for the alternatives to make it more greener and to reduce the E factor. So remember that for E factor, less is more. Okay, so E factor is the actual amount of waste generated in a process. It includes the chemical yield, the reagents, the solvent losses, and all other process aids. It do excludes water, because if we include water also, then kind of the effectors, they become quite large. So but we do take into account the organic or inorganic compounds which are dissolved in water. Okay, so we don't include water, but whatsoever is dissolved in that, we do include that in the waste while calculating the E factor. E factor is treated as an additive quantity for multi-component reactions. So if you have like a multi-step synthesis, where one step, then you have a second step, third step, and onwards. And if you have to find out the E factor for the total process, then you you uh, you add all the E factors for the different steps. So it would be the summation of all the steps. So this is a table which was published in 1992, and I have taken the snapshot from this particular reference of Green Chemistry Journal 2007, but this particular table was published in 1992, and it gives you the E factors for different industries like oil refining, fine chemicals, pharmaceuticals, etc. And we can see that as we move from oil refining to bulk chemicals to fine chemicals and then to pharmaceuticals, E factors keeps on increasing. For oil refining, it is less than zero point 0.1. For bulk chemicals, it is in the range of 1 to 5 or less than even that. Fine chemicals, 5 to 50, and pharmaceutical, 25 to 100. So if we look carefully at that, it is kind of increasing. So obviously the question which comes to our mind is, why is it so high for the pharmaceutical industry and so low for the oil refining? So if we can recall, like in oil refining, we use all the fractions which are used, which are created when you're doing the refining process. We use whatsoever is generated from that. That all is useful. Nothing is waste. While for the pharmaceutical industry, the APIs, the active pharmaceutical ingredients, which are the target compounds in the pharmaceutical industries, they're quite complex molecules, and their synthesis involves several steps and thereby generating lots of waste. Sometimes the pharma people, they say that since the product tonnage or the amount of the products which are generated is quite low, so this E factor is actually not the absolute one, it's quite low because we are creating less amount of the products. But this cannot be used as an excuse for generating waste. So careful consideration of the synthesis processes which we are using for the creation of APIs, a careful scrutinization of every step should be done. The methodologies need to be revised while keeping in view the green chemistry principles to reduce the E factor. So E factor include all reagents and 10% of the solvents as well. Here they are imagining that 90% of the solvents which are used in the synthesis, they are either recycled or recovered. And this is kind of uh, not a practical thing, because we know that when we do the synthesis in our labs, when we do the multi-step synthesis, for each and every step, we optimize a different solvent depending upon the reaction conditions and depending upon the requirement of the reaction. So if we start recovering the solvent from each and every step, there are there are greater chances of cross contamination of the solvents. So although we can say that 90% of the solvents are recovered or recycled, but it is really possible. So water is generally excluded, but actually disposal or recycling of the water also requires some pre-treatments, pH adjustments, or adding some chemicals to do the treatment. So to make it look more simpler, they introduce the term simple E factor and complete E factor, where the simple E factor takes into account all the waste except the solvents and water, while the complete E factor includes all the waste, all the water, as well as solvents used in that. The actual E factor, it lies somewhere between simple E factor and complete E factor, because if you provide the data that this much solvents I have recovered or reused, then then we can calculate the actual E factor. So for calculating the actual or the true E factor for a reaction or a process, the data must be provided so that it can be calculated. Now, talking about the system boundaries, so the background of that. So what happened is, when the things are highlighted in that table that the E factor for the pharmaceutical industry is so high, so in order to reduce the E factor or kind of greenwashing the image of that particular company, what they did is they start buying the intermediates and using them as the starting material, and thereby claiming that the E factor of that process is significantly reduced. But actually, this is this is not the truth. So just to give you an example, suppose we are conducting a synthesis where A and B are the reactants. They are reacting under suitable conditions to give products C and D, of which C is the desirable one, and it, under suitable conditions, transforms to a product E, which reacts with F to give the end product, which is G. Now, the E factor for this multi-step synthesis would be the summation of E factor for this particular step, this particular step, this particular step, for all the three steps. So if someone buys directly C and conduct this synthesis, of course their E factor would be reduced. But waste is definitely generated because C is synthesized somewhere else. It may not be in your manufacturing unit. It may, but it is happening somewhere on this planet. So it is obviously adding to the waste. So what should be our boundary conditions? Should we consider a cradle to grave approach, like right from the synthesis of every starting material to where it ends actually in the environment? Or should we adopt a gate to gate approach, that what is coming inside a facility or a plant and what is leaving that facility? So based on that, if we calculate the waste and the E factor. So for calculating the E factor, we use gate to gate approach, but we do need to define the starting material in order to clear the ambiguity which is there about, like, is it an intermediate which they are buying, or is it they're doing the synthesis, because that thing should be clear. So to define the starting material, this is the definition: a material that is readily available at a price less than $100 per kilogram from a reputable commercial supplier is considered a starting material, and for that you need not to take into account the E factor associated with the synthesis of that starting material. But if the price of that material is more than $100 per kilogram, then it is considered an advanced starting material, ASM. And while calculating the E factor for such a process, we have to take into account the waste which is generated for the synthesis of ASM. Okay, so this is just to make the comparison on a level playing field. So that's why we are doing this. Now, there are several other questions which arise while calculating the E factor, because waste is always not liquid and solid. It can come in the form of gases. There are emissions also, like the greenhouse gases, carbon dioxide, methane. They are emanating from the facility when you're using electricity, of course, for carrying out heating, stirring, cooling of the reactions. So if you take into account these emissions also, like the greenhouse gases, etc., then we call it E star, or E with the steric factor. So again, I'm repeating that it is treated as an additive quantity. For a multi-step synthesis like this, the E factor for the complete process is the summation of the E factors of all the different steps which are involved in it. Now, there is one more question which comes to the mind, that E factor do take into account the environmental impact, like the waste is generated, but it never talked about the nature of the waste. So we will discuss about this, like the focus is only on the quantity of the waste, not on the toxicity or the hazardous nature of waste. That we will discuss in the next lecture. Thank you very much.